In this video, I'm going to show you how to deal with distributive loads in statics, how to reduce them into a single force resultant. So firstly, what is a distributive load? We all know what a point force is, right? A point load, something acting at a single point. So let's say if I was standing on top of this big tower here, I would be a point force acting on the tower down, right? And you would know how to draw the free body diagram for that. Now, a distributive load is a little bit different. It's a lot different, actually. It's a ton of point forces acting across a surface. So it's a loading that is distributed across our surface here.
So as you can imagine, the force exerted by the wind onto our structure here is much different at the top of our structure than it is at the bottom of our structure. Actually, it's different all across the surface of our structure, right? But we know at the top, the force exerted by the wind is much greater than it is at the bottom. If you ever have stood on the top of a building or on top of a tall balcony in a hotel, you would know this. And as you can see, it's distributed across. This is what a distributive loading is.
Now, in order to deal with these loadings, you must reduce them into a single point force at a location. And that location is very, very important because that location is where our point force is, our force resultant that happens to be a point force, is equivalent to our distributive loading. So in order to find this force resultant that represents our distributive loading, we need to figure out its magnitude and its location. And to figure out its magnitude, we actually need to integrate. We need to find the area under this curve. Now, we are not going to deal with problems like this, at least right now. Problems that you're going to see are going to have distributive loadings that are in shapes that are easy to handle. Taking a long integral is not going to be something you're going to need to do in this. You're going to have distributive loadings that look like rectangles and triangles. So the area under the curve is represented just by, either the length times width, or in terms of a triangle, so it would be 1/2 the base times height, right? So in order to find a force resultant for these distributive loadings, you would need to find its area and then the location of the force resultant. So let's get rid of this, and I'm going to discuss how to do that. So as you can see, these distributive loadings are not some complex, shape. They're not some function, some curve, whatever. You don't need to integrate. We can just find our resultant force by obtaining the area of these shapes. And when you're given basic shapes like this, our distributive loading is represented not by a function, but by an average of our distributive loading. So per 10 kilonewtons, there is 10 kilonewtons of force per meter along our beam here on average. So in order to turn this into a resultant force, we must multiply this by the length, because it's a rectangle, right? We have a beam that is 8 meters long, just doing an example here, and our height is 10 kilonewtons per meter. So we would do 10 kilonewtons per meter times 8 meters. Meters would cancel out, and we are left with just kilonewtons, meaning we are left with force. So our force resultant is equal to 80 kilonewtons. Easy enough, right, to find the magnitude, but we also need to figure out where it's acting. Where is the force acting that is equivalent, that makes it equivalent to our distributive loading? Well, for a rectangle or a square, it's really easy. It's just at the midpoint. So this is acting along the entire beam, and the beam is 8 meters. So our midpoint is actually 4 meters, 8 divided by 2, right? So it's acting at 8 over 2, which is equal to 4 meters. So you would place this force, I'm going to do it in red so it's easier to see. You would get rid of your distributive loading and you would replace it with a resultant force called Fr that's equal to 80 kilonewtons right in the midpoint of that distributive loading. Very easy for rectangle. Now let's move on to a triangular loading. So what if our distributive loading was a triangle? We are going to do the same process, but our area is going to be different, and the way we find the midpoint of this triangle is actually different. So we're given that W of x is on average 5 kilonewtons per meter. So to find our force resultant, we need the area of Wx. So our distributive loading has a height of 5 kilonewtons per meter, and the area of a triangle is 1/2 the base, right? So 1/2 the base, which is 8, times the height here, 5 kilonewtons per meter. And that's going to equal, so 1/2 of 8 is 4, 5 times 4, that's 20. So we have 20, right? This is meters, so these meters cancel out, and we have 20 kilonewtons of force. And that is our resultant force equivalent to our distributive load. Now, to find the location of this, we can't just take the length of the beam and divide it by 2. It's not a rectangle. The midpoint of a triangle is actually represented by 1/3 the base from the tall side of the triangle. So this would be from the right side going left. You would go 1/3. So the base is 8 meters. So this would be 8 over 3 meters. And it would be, somewhere over here. And that would be our force resultant. We would get rid of this distributive load and replace it with that. And that's basically how you deal with distributive loads for basic shapes like this. In the next video, I'm going to cover an example that combines everything we have learned about statics so far into one video. Thanks for watching. Please subscribe and have a great rest of your day.